Okay, so this is lecture 6. We are still working on MOS transistor theory. So let's go to our previous lecture contents. Yes, in our lecture 5, we have learned how can we express our long channel IV characteristics. And at the beginning, we have learned that one of the most important quantity of a given technology is oxide thickness, because oxide thickness determines this oxide capacitance, so which is given by oxide permittivity divided by oxide thickness. So thinner oxide gives you higher oxide capacitance, and this oxide capacitance just to collect your electron, inversion electron or inversion hole in the case of MOSFET. So by applying this formula, so if you have higher gate overdrive voltage, so in this textbook we use this kind of notation, but whatever, this is gate overdrive voltage multiplied by oxide capacitance, then that determines the number of electrons or charge underneath the gate region. So of course here we have to multiply W and L in order to calculate the real charge in the unit of Coulomb. However, we more prefer to consider the aerial capability to collect electrons. So actually this COX itself is important. Then in turn, and now oxide thickness is so important. So when we have a look at the progress or evolution of CMOS technology, always TOX, oxide thickness, has been reduced considerably, and so later we will have some time to discuss about what happens to the oxide thickness. But anyway, so now we understand oxide thickness or gate capacitance is important. Once we understand this one, then now we can understand we have three different operational regimes like subthreshold and linear saturation. Of course, the distinction between this subthreshold and linear saturation, this is based on your gate source voltage. So when you apply low gate bias, then your device is in subthreshold region. However, if you increase your gate voltage, then you enter into linear mode or saturation mode. So in these cases, we have non-zero drain current. Okay, that is positive in the case of our MOSFET, and in the case of these two cases, still we have a distinction according to the drain voltage. So if we have low drain voltage, then the device is operating in the linear region, and if we have sufficiently high drain voltage, then the device is operating in saturation region. Okay, that was the lecture content we have studied in the previous lecture. So in the previous lecture, the derivation was not completely shown because I gave you just a qualitative explanation on it. So I wanted to make the full description about the derivation procedure. So at any position x, so x means that starting from 0 to L, wherever you are, then you have the channel potential and gate overdrive voltage. So that determines the number of charges collected underneath the gate oxide. There you have to multiply W to consider the width of your transistor, and what is it? This was the velocity. So velocity according to your drift operation. So now, although we can write it down as a function of our position x, actually it should be constant. So although in general it can be a function of x, however physically it should be constant. So what we do is just to integrate it, id, treat it as a function of position and integrate it over from 0 to l. Then what will happen? Since it is just a constant, then we will have constant multiplied by our length L. And of course, this constant means that constant ID value. So now you can see that here we have L times ID as a result of integration from 0 to L. And the right hand side is now integrated. So please have a look at this form. Now you have this mobility, oxide capacitance W. All of them are just constant, so we can pull them out. Then only remaining thing is this voltage dependent term and this first order derivative taken from our velocity. Then now here you can see that here, and then we can now change it, the variable, integration variable from dx to dvc, channel potential. After that we can make a simple integration. We have done it already. So this is constant, so the constant and dv gives you just linear term, and here we have vc and dvc. So vc dvc, so when we integrate it, then it gives us so half of squared vc. So that was the integral, and now you can see that here we have L, and eventually this L is divided. That's the reason why we have eventually ID equal to mu n Cox W over L and blah blah blah, and that describes the dependence on your drain voltage and gate voltage. That was done for linear mode. And what will happen for saturation mode? Then in that case we try to find out the maximum value according to this description, and we believe that beyond that point then we have to have the constant value for saturation condition. So what was the condition for saturation? So simply speaking, so drain voltage for saturation was given as VGS minus VT. So gate overdrive voltage. So do you remember? Also, when we have saturation mode, what was the ID? So ID was also given by ID. Saturation was simply given by half mu n Cox W over L and Vg minus Vt, it's square. So this is nothing but gate overdrive voltages square. Okay, so this is a simple review of our previous lecture, and we have spent quite a long time to discussion how can we integrate this form. So but it is just a simple reminder how can we do that. Then now let's cover the remaining content of our long channel MOS IB. Then let's go to more realistic non-ideal effect of our MOS IB. So you have already the homework on drawing input characteristics and output characteristics of your transistor. So input and output characteristics of your transistor is fundamentally important when you consider your device. So it is quite much important. So please have a look at it. So device engineers always draw these two types of graphs. So one is so-called input characteristics. Here, why we call it as input? Because in the case of MOSFET, so gate is treated as input terminal and drain is treated as an output terminal. So input characteristic simply means that what happens if we change the input voltage. In other words, gate voltage. So here we have gate voltage as a variable. Then we measure the drain current. So this is one. Then maybe you can easily draw these graphs using all of these given parameters. So simply speaking, beyond the threshold voltage, here you have 0.3 volt. Now you have a non-zero current, and here now you have a non-zero current, and you have almost vanishing current here. And also, people takes two different voltages. Here we have one value and another value, and this is, although this is 1.0, but this is not fixed. Actually, this value should be the value of your VDD. So when you draw input characteristics, one you have to draw is when your drain source voltage is VDD. This is one condition you have to have. And this does not show everything. You have to also draw another one, VDS, and this should be a small quantity. Like typical value, sometimes people takes 0.1, sometimes people takes 50 or 10 millivolt. This is corresponding to 0.01 volt, whatever. So there is no standard, so you can select any of them. But anyway, they have to make a comparison between this and that. It is important. Not only one drain bias, but you have to consider two different biases, and one should be high, one should be low, because later we want to see the difference of these input characteristics with respect to your drain voltage. So this is the one. So maybe you can easily draw this one. Then this is linear graph. So y-axis is written in linear, and this is written in linear. Good, but however, in this case, in this input characteristics, more important one is this semi-logarithmic graph. So in this case, you have to have y value, drain current written in logarithmic scale, and here you have linear scale still gate voltage. So in this case, now you can find a certain behavior, and according to our simple equation studied in the previous lecture, simple lecture, below the gate, below the threshold voltage, we have no current. That's the reason why we have really steep behavior shown here. But as I stressed here, this is completely low. So please, this is completely low. So in the linear scale, it's okay because it is much smaller than other currents observed in this case. However, this is really completely low. So what is the realistic one? In the realistic case, the graph should be written or drawn like this. So it's okay. This part is okay. However, we have, sorry about that. So we have to have something like this. So there, of course, here this one has a certain linear like straight line like slope behavior, and this slope is actually very important. So I'm not quite sure I have done it properly, so we will see it later. But anyway, here we have assumed that in our simplest model, we have assumed that ID equal to 0 when gate source voltage is lower than threshold voltage. Okay, in the first order, it's okay. However, in realistic case, this is far most important quantity. So don't be fooled by this simple model. Always, even in the sub-threshold region, we have certain non-zero current. Then the amount of that non-zero current is quite important in our realistic design. Okay. Then let's go to second one called as output characteristics. So now you easily guess what is the output characteristics. Now output terminal is a drain terminal. So now we have to draw ID as a function of VDS. So as pointed out by our student, one of our student. So this is my typo. So please understand. So this is a drain voltage, so you have to have a drain voltage and you have still drain current as a Y value. So the drain voltage starts from 0 and ends at your VDD. Okay, so here you have also graphs, and this the highest one is corresponding to also VDD, and here you have certain intermediate values, so it really depends on you. So I rather prefer to have a 0.9 and 0.7. It's your choice, and I want to have just 2 volt spacing. It's okay, but anyway, so please draw in this way. Then now you can easily understand this is maybe the knee point for transition. So here you have linear mode, and beyond this value you will have saturation mode. And where can you find the knee in the case of gate voltage of 0.8 volt? Please guess. Maybe you have somewhere here for transition between linear mode and saturation mode, and here you have it. And wow, it is difficult to see, but maybe somewhere here. And one important thing is, if we just collect them all, you can find that here we have something, and here we have something, and here we have something, and here we have something. Oh, so what happens if we just connect them? Then you can find they looks like a parabola. It is because what is their x position? Their x position is the voltage for saturation mode. So that point was given as VD set was given by our gate overdrive voltage. Do you remember? Also, what is the y-axis? Y-axis is corresponding to ID set, saturation current. And if you remember correctly, then saturation current was given by half beta multiplied by squared gate overdrive voltage. So that's the reason why its y-axis is corresponding to square term of gate overdrive voltage, and its x-axis is corresponding to the linear term of our gate overdrive voltage. So when we just connect these transition point all together, then we will see parabolic like one. This is typical behavior of our long channel MOSFET. If we have a long channel MOSFET, we have such a kind of behavior. Okay, we will consider this behavior today once again. Okay, and also whenever you have any question, then please interrupt me. Then before going into the short channel effect or non-ideal effect, so I want to briefly discuss about capacitance. So capacitance means that, of course, we have already discussed about capacitance. Wow, what was the capacitance? That was given as Cox, and that was given by oxide permittivity divided by oxide thickness. Why do we have this kind of thing? It is because we have a metal and we have T thick oxide layer and we have a silicon. So that's the reason why we have a COX. Now it means that this one COX just to describe the capacitance between this metal and channel region. However, this is not the only structure inside our transistor. Please add more components to have complete description about your MOSFET. So you have to have, for example, here so-called source region, which is typically N plus region in the MOSFET, and you have also drain region. So as you can see, between metal and silicon channel, we have the COX. However, since this is another silicon, then maybe we can have the capacitance between gate metal and source, and capacitance between drain region and metal. So these kind of capacitance can exist inside our transistor. Also, we have another one. In order to realize planar MOSFET, we have to have p-type substrate in the case of n MOSFET. Then now this one is given as what? Given as usually highly doped N plus region and highly doped N plus region. So now we have a certain structure called PN junction because this part is p-type and this part is n-type. And what is the bias condition between this source and substrate? Usually substrate is grounded. How can you make a ground? So usually, in this case of a realist case, here we have the N diffusion for this source, and here we have another one like P plus region, and this part was called as a tap. So here this is connected to the ground, and through this line even our p-type substrate is biased to the ground. So now this p-type substrate is always biased to the ground. However, source is also grounded. In this case, what is the voltage difference between source and p-type substrate? That is 0. So we can say that between source and substrate, the applied voltage is 0. In this case, of course, sometimes the source voltage can be elevated. However, in this simple case where source is grounded, then this is 0. And please consider the source instead of a source. Please consider drain case. In this case, usually this drain voltage is used as your output logic signal. Why? Then this is typically non-zero, so sometimes it can be either 0 or VDD. So let's say that we have a VDD case. Then what happens? Now p-type substrate is biased with 0 volt and n-type drain region is biased with VDD. Then which one is highly biased and which one is lowly biased? VDD is a positive number, so we can say that n-type is highly biased and p-type is lowly biased. In this case, when p-type is lowly biased, then this structure called PN junction do not conduct current. there is almost negligible current or no current, and this PN junction is just acting as a capacitor. So also, even in the case of a zero biased case, this one gives you just a capacitance. So simply speaking, when we consider the entire MOS structure, not only the oxide capacitance, the capacitance between metal and silicon substrate, but also we can find more elements like the, the capacitance between gate and source, gate and drain. Also, another one corresponding to substrate to source, substrate to drain. They should be considered in our actual calculation. Okay, so simply speaking, any two conductors separated by an insulator have capacitance. Yes, so gate to channel capacitance, this is Cox, so we have already seen it. But another one is source drain has also capacitance. So this is called as a diffusion cap, because this is previously it was made by the diffusion process, but anyway, due to historical reason we still call it as diffusion reason. So now let's go to our figure, and as I explained up to now, here we have the capacitance, and this is corresponding to Cox. Once again, Cox is, although oxide capacitance, this is not exactly capacitance itself. This is capacitance per unit area, and just multiplying the area, the drawn area of our metal, then we will get the quantity corresponding to farad. So maybe you remember that we have already calculated the value, and it was extremely small, like just a few femtofarad, and for a very large case like 1 micrometer and even 1 micrometer, the capacitance was so small. And in the realistic case, we have much shorter length and much narrower width. So the actual capacitance of our transistor is extremely small. And another one is we have overlap capacitance. So that is nothing but the capacitance between this one and capacitance between this one. Is gate overlap capacitance. And another one is diffusion cap. So simply this is the capacitance with respect to the body substrate contact. So I made mistakes, so I have a typo, so not source, but of course we have to have drain. So capacitance between body and source and body and drain. Then let's go to this figure 2.8. Then what happens? Here we have two transistors and connected. Then you can see that here, although the structure, if we draw it as a just same, if we draw in a schematic way, then they will share the same schematic. However, you can see that we have different structures. Then please consider what will happen to these three different cases. So since the area is smaller than this larger one, then the capacitance between this diffusion region and our substrate will be decreased. Okay, so are we doing? I mean that. So let me just draw in this way. In this way. This is corresponding to your lower MOSFET, and it has something. And this part is corresponding to your top MOSFET, and they are shared. This this shaded region is also shaded here. And if you have, in this case, this length is 3 times lambda, and if we have a longer device, like instead of this 3L, let's say that 5 lambda, then what will happen? Then since we have more area consumed by this diffusion region, so what we can expect is now the capacitance between this capacitance between this substrate and this region, so diffusion region, can be increased by factor of, in rough sum, just this. Okay, if we have a wider structure, then since the area is increased, so we will have more capacitance. So this is just a simple estimation of increase of capacitance, but actually what we can find is so the capacitance between substrate and any other diffusion region, in this case a source, but this is also true for drain to body capacitance, so please understand this one. And this is corresponding to this simple formula. This simple formula means that in previous discussion I told you that if we make a wider structure, then we will have more or higher capacitance. It is quite understandable, but you know that the area dependence is given here. If you have twice wider, then twice wider area, then your capacitance will be doubled. That is described by this vector. However, here you have another term. And what is this PS? So AS, in this notation, AS is corresponding to area of your source region. So since we are, for example, if we are talking about the drain region, then we have to have area of drain region multiplied by capacitance between body and drain. So that is area dependent one. And here we have another quantity like PS. What is it? This is the perimeter of your source. I mean that, let's go to this one here. Let's say that this is your drawn diffusion. Yes, I have drawn a diffusion region whose width is 4 lambda and its length is 5 lambda. Then maybe you can expect that, okay, if I just increase it double, like 8 lambda, then what will happen? What we can easily expect is, compared with this 4 lambda times 5 lambda, since we have now 2 lambda times 5 lambda, now we have doubled area. So maybe we can think that previously we had a certain kind of value C diffusion, and now we will have the quantity like 2 times C diffusion. This is area dependent one. This is our first guess. However, this formula just states that capacitance is not only dependent on area, also dependent on what? Also perimeter. So previously we had a perimeter of this diffusion region corresponding to what? So that was 18 lambda. Are you with me? 4, 5, 4, 5. That was the value of perimeter. However, if we have a doubled structure, then what happens? Here we have still 5 lambda 5 lambda, and 8 and 8. So eventually we will have a perimeter of 26 lambda. It is not exactly doubled, so slightly lower than that. So exact behavior of your diffusion capacitance for this enlarged system is not exactly doubled, and it has a little difference from this expected only area dependent prediction. So please have a look at it. But why do we have this kind of two different behavior? Why one is area dependent and why one is perimeter dependent? It is because when you draw something, so let's make a cross section, then usually when we say certain area, then that area is corresponding to the main body of our diffusion region. So let's say that this is your diffusion region and this is a substrate, and the area just to describe the component corresponding to this junction. However, also you can see there is although not that high compared with this main body, but anyway, there is certain part and certain part connecting diffusion and substrate through the side direction, not this vertical direction, but lateral direction. We have also still connectivity that is described by this perimeter dependent one. Okay, so that's the reason why we have two different dependencies for this capacitance. So here we have example 2.2. Please do your exercise. So
PN 정도는 공필 영역에 해당하는 capacitance, PS에 해당하는 영역이 PN 정도에서 발생하는 공필 영역의 경우에
both of, okay, it is a really good question. So he asked me, so is it related, this phenomena is related to the depletion of a PN junction, and especially for the case of this perimeter dependent one? My answer is both of area dependent one and perimeter dependent one are related to the depletion of this PN junction. So actually, so since your question is so good, let me just explain a little bit further about that. So now usually we have substrate and its doping density is not that high, and diffusion region has a much higher density, doping density. So when we draw the depletion of depletion area of this transistor, then usually only this p-type substrate is depleted, and the amount of depletion inside this entire region is extremely small, and this depleted area is working as just insulator contributing to the capacitance. So even in this area dependent one, the physical origin is depletion of your PN junction, and even in the case of this perimeter dependent one, still the physical origin is depletion of this side wall. Okay, this side region is also depleted. That's the reason why you have perimeter dependent contribution to your gate capacitance. So simply speaking, both of area and perimeter dependent quantities or contribution to the diffusion capacitance are originated from the depletion of your PN junction. But since you have always have this side one, you cannot eliminate it at all. So this is something that was a really good question, and I really encourage all of you to give me such kind of a good question. So please do your exercise using homework 2.2. Of course, then who decided this value? this is a perimeter dependent one, and this one is an area dependent one. Actually, you cannot predict it. So your technology guy should provide you, okay, this is my technology, and according to my measurement, I found that this value is given by something like this one, and this value is given by something. Please consider these quantities when you design your device or your circuit. That is the situation. So as a designer, we have to accept these given parameters, and based upon that one, we have to, in many cases, minimize the capacitance related with this diffusion region. Because why we have to have reduced capacitance? Because this just delay the speed of our circuit operation. Okay, that was a really simple description about that one. Here I have one thing to tell you. Here we have a source and drain. Once again, now you understand, between source and substrate you will have a capacitance, and between here drain and substrate or body you will have the capacitance. Let's assume a symmetric structure as usual, so you have the same size of source and drain, and let's say that you apply 0 volt and VDD to your drain. Of course, this gate voltage is taken as so small, so 0 volt, so nothing happens between source and drain. Then what will be the capacitance between drain to body compared to the capacitance of source to body? Which one is larger? So please think about this one. This is reverse biased PN junction. Reverse biased PN junction. And when PN junction is reverse biased, then the distance between your N plus region and P region becomes widened. So at equilibrium or 0 volt, you have this distance, and when you have reverse biased junction, then you will have thicker depletion region. Then please consider what will happen to your capacitance. Then let me just move to the next topic. Okay, so up to now we just considered ideal IV characteristics and capacitance, quite a simplified one. But unfortunately, we are always trying to use the minimum sized devices, especially in the case of length. We wanted to take the shortest device. Then this shortest device has somewhat different behavior compared with the device with longer channel. For example, in the case of, let's say that 65 nanometer IBM technology. So this is also somewhat old, but anyway, in those days, the channel length was about 50 nanometer. I mean that the shortest available gate length was 50 nanometer. And let's say that you have 1 micrometer device fabricated under the same technology. Then in the case of this long channel device, then you will find that your long channel IV characteristics predict the measured data quite well. However, unfortunately, when you go to the limit of your channel length, the shortest one cannot be well described by ideal IV characteristics for long channel device. That was the problem. So Actually, this is nothing related with measurement data, but they did some computer simulation. So blue line is corresponding to the computer simulation. However, this computer simulation is well matched to the realistic data, realistic measurement. And this black curve is obtained from our long channel IV characteristics. So when we predict the IV characteristics of a MOSFET with long channel IV characteristics, then we will find that, okay, we will predict that when we apply 1 volt case, then we will have such kind of a high current for this device, around 1200 microamp. However, more realistic estimation gives us this is just 2/3 of the predicted one. Okay, so this is the value. Okay, sometimes you feel that 2/3, that is not that bad. This is quite close to 1. However, please note that in the case of device engineering, they are really hungry for performance. To them, 5% difference is really matter of death or alive. I mean that this is really critical. 5% difference is so critical. So you know that nowadays every technology node, your improvement is not that huge. So this 2/3 or 1/3 reduction of IV characteristics due to the long model is quite important. Okay, so this is too severe failure of our prediction. So why do we have such kind of huge reduction? That is one thing we have to ask to ourselves. Another one is related with this one. Black curve is ideal IV characteristics, and previously I asked you, please try to find out the transition between linear mode and saturation mode. Can you do it once again? Then maybe you can find that maybe this is the transition reason, and this is the boundary between linear and saturation, and maybe this is one, and maybe this is the one. So once again, when you connect them all, then you find that this is more or less parabolic. So when you apply your gate voltage higher and higher, then what you expect is, okay, my saturation current increase quadratically with respect to, so simply speaking, my saturation current is quadratically dependent on the gate overdrive voltage. That is our expectation following the long channel IV characteristics. Then now my next question is, instead of this idealized one, please try to estimate the transition point for this realistic blue curves. Where do we have the transition? It's not that easy, because in this case we have the perfectly flat region, so it was quite easy. But now we have a non-vanishing slope, so it is not that easy. But anyway, you may think that this is the approximate point for the transition, because our linear lies graph is over. I mean that here we have almost a straight line, and it is now gone. So here you can see that. And when we have this one, also you can find this kind of behavior. Well, when you have a look at this one, between 1.0 volt and 0.8 volt, previously in the case of our long channel device, long channel description, the difference was somewhat large, and when we compare the difference between 0.8 and 0.6, so please have a look at it. Which one is larger? Is this larger or is this larger? Obviously, between 0.8 volt and 1.0 volt, we have a larger, higher increase of drain current. Good. It is because we have this kind of behavior. But please have a look at these blue graphs. And here, the textbook quite kindly describe this behavior. Please have a look at this increment and this increment. This is increment between, once again, 1.0 volt and 0.8 volt, and this is 0.8 volt and 0.6 volt. What is your opinion? Is this larger or is this larger? Well, it is difficult to say, but at least we can say that they are comparable, not increasing any further. So saturation current, I mean that not saturation current itself, but increase of saturation current is not increased any further. So that is the second point we have to consider. Finally, we have, as we have already seen it, the blue curve has a non-zero, non-vanishing slope even in the saturation region. So this is the one we have to consider in this lecture. Of course, maybe time is running out, so I hope that we can consider the first two parts in today's lecture, and this third one, the last one, will be discussed in the next lecture, and please have a look at it. But before talking about this kind of behavior, why we have this deviation from long channel IV, but I wanted to ask you, please concentrate on these two quantities like on and off current. This is important, on and off current. Since we are working in the digital scene, so actually the gate bias we can apply is mainly either 0 or VDD. Also, drain voltage we can expect is also maybe 0 volt and VDD. So we can consider more or less 4 different operational points. So are you with me? Then let's make these 4 configuration. 0, 0, let's say that this is VG and this is VD. 0, 0, in every device, when you apply 0 volt and 0 volt to gate and drain, what is your expectation for your drain current? This is just useless and there will be just 0 ampere. So no way, we don't have to quantify. And now let's say that we apply VDD and 0. Now we have a fully turned on device. We have a lot of electrons beneath the oxide region. However, the driving force for drain current is still 0. So still we have 0 ampere. So in these two cases, we don't have to care about that. Then the remaining 2 different operation points are drain voltage is kept as VDD, the maximal value, and gate voltage is changed from 0 to VDD. So this first one corresponding to gate voltage is 0 and drain voltage is VDD is called as so-called off current. In ideal case, this off current should be 0 because the gate terminal which controls the current says that, oh, this transistor should be shut down. However, unfortunately, we have non-zero value. This is certainly higher than 0. Then this amount of I off really describe the degree of failure for shutting down this transistor. Okay, so it is good to have the value close to 0. However, it's not possible, so we have to say that anyway we have to quantify this I op value. So this is critically important one, because this I op just to describe the failure of our op condition, and this determines the op state power consumption. And another one is VDD and VDD. Now we wanted to turn on this device, and it was turned on, and it tried to conduct its best, and the best performance or the most current it can conduct is described by this ion. So now you have to understand we must quantify these two currents, I op and I on. Then where can you find this I on and I op? One thing you can see is when you have this output characteristics drawn in the left figure, then please point out the point for your ion. You can easily point out the ion point is corresponding to this point, where you apply the highest drain volt and where you apply the highest gate volt. So output characteristics, you can find it. Then my second question is, where can you find I/O in this case? Unfortunately, it is not easy to quantify I/O in this left figure corresponding to output characteristics. It is always 0 in this case, because we are now looking at the current in the linear scale. So this output current does not give us the exact information about what is I/O. However, this is best suitable for quantify I/on, because I/on is shown in the linear scale. Then please move to the right figure. In this right figure, what is it? This one gives you the input characteristics of your transistor, and drain voltage is kept as VDD. Wow. Then in this case, you can easily understand this point is corresponding to your I on, and this point is corresponding to your I off. So this figure, the input characteristics written or drawn in this semi-logarithmic scale is best suitable for visualizing both of on current and off current. Of course, I want to say that only for I-on current, it's not best suitable, because in the case of I-on, we are very sensitive to just 5% difference or even 3% to 1% difference. However, in this logarithmic scale, this percent-like difference cannot be visualized quite well. This figure is good when we measure the difference between off and on, or sometimes visualize off itself. In the case of off, we are not very much care about, for example, 10% difference of this one, nanoamp per micrometer, or 24 nanoamp per micrometer. Actually, we are not that much interested about this 10% difference of I-op, because I-op really changes orders. Its orders are different. Sometimes here, depending on your technology, I mean that even for the same technology, you can have a lot of differences depending on your device option. Okay, I will explain later. But anyway, what I want to say is I-on and I-op are two most important quantities to quantify our transistor's performance, and I-on is related with the maximum current, and I-op is related with the undesirable current, leakage current of our system. So what we wanted to have is maximize this difference. It's good. Maximum difference is preferred, and also this one should be maximized and this one should be minimized. I'm saying that seemingly redundant one. So I have shown you three different ones. I ask you to maximize ion and ion. Sounds good. And increase ion. Sounds good. And increase ion. Sounds good. Decrease ion. Sounds good. But you know, these three cases are all good cases, but in one transistor it is extremely difficult to be achieved. So sometimes people should satisfy one thing. One option we usually take is, okay, I will just take this one. I will maximize the current. Then obviously there is no hope for us to have low ion. So this transistor, so-called high performance transistor, will conduct a lot of current when it is turned on. However, unfortunately, when we turn it down, still we will have a lot of current, leakage current. That is one option. On the other hand, we can have low power thing, means that we have extremely small of current. Then there is no hope for us to have powerful device. Then they should have lower of current. So are you with me? It's like a car, shopping a car. So you visit dealer shop, then you wanted to buy something. So you have a limitless amount of money, so you can buy anything. But there are two cars. One car is a very luxury car, and it is quite fast. However, its gas efficiency is really poor. Or you can buy a very small car. It's not that fast. Its acceleration is poor. However, it is very gas efficient, and you can run that car quite long. And once after you give some certain amount of gas. Okay, so are you with me? So you can understand there are many different options for our transistors. So now let's have a look at a realistic example like Intel 32 nanometer transistor. It was the state of the art about 12 years ago or 10 years ago, and it shows many different options like high performance and low power, and in between we have standard one. It's quite much reasonable. One is heavily focused on only for performance. I mean that this one is focused on current, and this one is highly focused on off current, and we have something like a balanced one, not that much powerful, not that much leaky. So that is called as a standard one. And as you can see, please have a look at your MOSFET. The MOSFET graph is shown here. And in the case of this high performance option, then you can find that, oh sorry about that, this x-axis is ID set. And what is the ID set? This is just ion in their notation. And in the case of this ID on and off current, then yes, you have quite high value of ID set ion. Then please have a look at this is once again same semi-logarithmic graph. On current is written in what? Linear scale, because on current is not drastically changed. And in the case of off current, it is written in the semi-logarithmic scale because it varies quite a lot. So simply speaking, think about two different cases. I mean that this is really interesting. So let's have a certain values, nominal values of your low power option and nominal value of your high performance option. So your own current is in this case, in this scale, about 0.7. And what is it? Now you have your values corresponding to 1.5, slightly larger. So what is the difference between this and that? You can find that the improvement of your own current is about just 2 times. In order to get 2 times in improvement for your own current, what you get is the increase of leakage current by amount of from 30 pico to 100 nanoamp. So this is 10 times, 100 times, 1000 times, and 3 times more. So you have sacrificed 3000 times of leakage current to get twice higher drain current. Do you think that this is reasonable? Yes, that is really reasonable. So for critical part, you have to have a really powerful device. So its leakage is not that important. Even though you have 3,000 times more leakage current, you are willing to pay that because you want to have a really powerful one. Okay, so that gives the designers many options. For performance critical point, you can spend the logic one, and for other ones that doesn't doesn't require such a high performance, then usually you can use more balanced one. Okay, so now you understand the trade-off between on current and off current is not symmetric, but people are really willing to spend more leakage current for higher performance for some cases, and they are, you know, that logic and standard and low performance just shows a certain line. Of course, this is slightly up the trend, but you know that they are well aligned in this case. It means that this line just describe their best given the technology, these are the best line we can achieve. So which one is better? Which one is the direction for performance improvement? If you have a more idealized device, then will you take this point, or will you take this point? What is the right direction for your performance improvement, technology improvement? This direction says that your device has a lower on current and higher op current. Means that it sucks. No, you should not use this technology. So always when you have a better technology, then your technology moves in this way when you draw on and off direction. Always it goes right lower direction. So then this is a better way when you develop a new technology compared with the previous technology. You draw this off and on diagram. Then you find that your technology is now located here. Then now you say that, oh, our current technology is better than previously available one. Okay, that is really interesting. And you know, this one just shows just 3 options, but nowadays we have much more options because, you know, previously there was only one tool, one technology, one device that was applicable to all cases. But unfortunately nowadays technology development becomes too difficult, so now they introduce more and more options. For example, in the case of Intel's another ID paper, just 1 year later, and you can see that even these low power logic options have divided into two part, two more. So yes, nowadays there are even more options. Please don't consider this part because this is high voltage one. It has a different oxide thicknesses to resist against the higher applied bias. So options like 1.8, 3.3, this is much higher. Usually the logic devices we have a much lower VDD, like a 0.775 volt at the time, and nowadays we are more or less fixed to 0.7 volt in these days, and we wanted to reduce it further. Okay. Do you have any question? So if you have any question,
VDD를 낮추면 좋은 게 있나요?
sure, that is a really good and good question, and obviously that is always good to have a lower VDD. So period. That's it. But why we have such kind of result? It is always related with power. Power consumption is proportional to this one. Your power consumption is proportional to square of VDD. So you know that when the CMOS technology was first invented, it was not for mobile devices. Actually, there was no mobile device at the time. So CMOS technology was used to fabricate, at the first time, mainstream supercomputers. After that, it was applied to make a PC. However, even in the case of PC, personal computer, you don't move it, and it is always plugged in, so it's not that much power hungry. However, since technology has evolved quite a lot, and later we have some need for mobile devices, and this mobile device is operated by batteries, and this is really power hungry. So when you have a look at the evolution of your VDD, let's say that this is year and this is your VDD, and for a long time it was just saturation as 5 volt. After that it starts to fall down, and nowadays we have 0.7 volt. Actually there are other reasons to reduce this VDD too. However, it is true that the main motivation of reducing the VDD is corresponding to the power reduction. So always, I want to say that always power reduction is one of the most important ones. So always people wanted to reduce the VDD. But unfortunately, okay, so time is up. So now we have only 2 minutes, but I will spend my remaining 2 minutes for answering more to your question. Well, we wanted to reduce VDD further, but why we are not able to VDD further? Like 0.7 is quite a low voltage, but why don't we have a 0.5, 0.3, 0.7? It's not possible in our current technology. This is given the answer. This figure shows you the answer. I mean that in order to make a digital device, you have to have a sufficient amount of on operation. This should be large, but please have a look at this one. In this technology, you have 0 volt and you have, for example, 0.3 volt. And in this case, what is your value? It's around 10 micrometer. and it is around 30 nanometer. How large is it? How large is the ratio between off and on current? 1 decade, 2 decade, and less than 3 decades difference. This is not sufficient to make any kind of reasonable device. So it means that if you reduce your device VDD down to 0.3, your digital system doesn't work. So unfortunately, in order to get, for example, 5 orders of magnitude difference, then you have to at least 1, 2, 3, 4, 5. Then your VDD should be such a large value. So now you can ask me this question, oh, Professor, if that is the true, this finite slope makes problem to reduce the current, then why don't we introduce a better technology whose shape looks like this? If we have such a brilliant technology, then even within small voltage difference, we can achieve higher on and off current. That can be asked by students, but unfortunately, this slope is set by nature. So we cannot make steep slope. There is a given limitation. So that's the reason why we cannot reduce our VDD value any further. Okay, that was a really good question. And since time is up, so I will just wrap up here. And originally, I gave you some homework problems, but unfortunately, the lecture did not progress up to that point. So I will just cancel out our homework 2, and the release of homework 2 will be postponed to the next Tuesday. Okay, thank you for your attention, and I want to wrap up today's lecture. Bye.